Hello, this is Jean-François Kalray. Very nice to have you here for this SDC 2021 presentation. I'm going here to explain how it's nice to have SPDK implementation on a manycore and many node system with comparison to a SPDK just running on one system. So how we took benefit of the parallelism. If I go into the details about the abstract of this presentation, yes, first I will cover what are manycore systems, how they have been designed, how we can use them, and then in the second part we're going to cover how we have implemented SPDK on the top of that manycore system. It's very much like having SPDK running on many nodes, many x86 type of systems with a current view from a user perspective. So this is quite unique because today SPDK implementation is just running on one node. What if you have many nodes, right? So this is about this presentation. About us, so I'm Jean-François. I'm Chief Solution Architect here at Kalray. I'm bringing in 30 years of experience in the data center industry, and specifically in the storage market. I'm here to bring innovation, to develop the new products, and to help think ahead in terms of the new feature we could bring, leveraging NVMe and NVMe, which are the new things, really the new protocols, to take benefit of the latest generation SSDs. My colleague Rémi Goguet, who is our senior software architect, will cover in details how SPDK could be implemented on a many-core system. So he's going to explain some use cases and what could have been done leveraging the SPDK package. So here's the agenda. This first part for the first 20 minutes is going to cover why many-core. Why do we need a many-core architecture or processor? Why do we need that change? And foremost, why do we need an open platform on the top of it? Why do we need an open platform for software? The second part of that presentation will focus on SPDK, right? So why have we chosen SPDK? How have we optimized SPDK for a many-core processor? What is specific to many-core? And then Remy will focus on use cases, right? It took three use cases on how we have taken benefit of SPDK module, so that is very well optimized on a many-core system. So let's get started on why we need a new type of processor, right? I suspect you're quite familiar with that. Data is exploding in many ways, but nonetheless, data is exploding. The variety of data is changing quite well, right? And the location of data is changing as well, right? There are so many new devices generating data, sorry. And I think we are all familiar here that edge is a massive change, right? And it's completely impossible to think about the next generation data centers having all the data in one place. Some numbers I show here that demonstrate that only 25% of the usable data will reach the data center, meaning that 75% of that data, of the overall generated data, will be ephemeral, will be compute somewhere, compute inline at the edge, but the edge could be everywhere. If you think about 5G, it could be at the edge of the antenna. Or it could be somewhere in between that antenna and the main data center, some edge data centers, small locations, right? Think about it. It's like with AI, right? You have so many devices generating data. You need to filter what you receive because the network, even 5G networks and 100 gig, 200 gig networks are not big enough to absorb that big amount of data, to treat that data in line fast enough to get a result. Because I think it's important, right? It's not just about the data. It's what you do with the data. It's how you treat that data to make something about it, to make something with it, right? So this is important that data is at the center, and we need to have the compute power globally to manage that data, to explore that data. What we see is the evolution of the computer. Obviously, you're familiar with the Moore law, right? Which gives the number of units you can get in a certain space. And we see that evolution. We have seen the evolution around computers from mainframe to open system to laptop, and then to smartphone in early 1990s, right? No more just like a phone, right? Something to run applications, to treat data at the edge from a user perspective in your hand, right? But what we see emerging in the past two years are really a new type of processing power, because it's about treating those emerging and markets, emerging new type of data, and this request to treat those new types of data in real time. And we have seen, and I will go into the details, that the traditional CPUs are not suited, have not been designed for that. So the industry need built from the ground up data-centric units really to treat that from the edge to the data centers in order to be very efficient and to treat inline data. So if we compare what we have on the market today, we have those multi-processor, multi-threaded x86 AMD-based type of processing power, right? It's well known, well established. Many applications are running. Those processors are generic processors. They can run many applications, right? But they don't have been designed to manage data. Then came GPUs, right? And NVIDIA participated a lot in terms of making GPUs more popular. GPUs are those graphical optimized systems or matrix calculation optimized system to treat in parallel many things, but really specific. So it's well suited for neural networks, right? Because those matrix multiplications, those mathematical applications can run very well on GPUs. But again, it's not a data-centric unit. That's why you need something different. And DPUs or many-core processor have been designed to treat data from the beginning, right? So it's a new type of architecture. It's non-blocking. When you think about doing things in line, what you don't want is, because one process takes the word processing power, that all other processes are completely locked. You need something real time. You need something predictive, right? You need to have quality of service in how you treat your data. That's why you need to think completely different on how your processor has been designed, right? We will see the details here. So this is an example. This is what we are doing at Kalray, right? Just to name one example on what a many-core processor is. So you need a core, right? Obviously, you need a core to do things, to treat things. And that core is associated with a mathematical core, right? So acceleration units, that's important. That core power has been designed to really treat data, to accelerate algorithms around data, to be very efficient for things like Reed-Solomon, for encryption, and you name it, right? All those new algorithms you put around data to put value out of that data. Then, obviously, you need more than one core, right? Here you see an example where we have grouped those core in what we call a cluster, which is a coherent group of cores. Here is an example of 16. It could be more, right? But this is what we have, and it gives an overview of what it could be done. 16 core. This is really the basic of the things. This is a unit on which you can run an OS, such as a Linux, such as a real-time OS. And you can port any of them. And then the processor is made of many of those clusters, of those group of cores. And the example we have here and the implementation we are currently running is a 5-cluster, a 5-unit type of processor. What links those units together is a common backend, and we have chosen Ethernet as a common backend. So any core, any cluster, any group is speaking natively Ethernet. So it's easy to think about more of them, right? So you can connect more cores into a bigger cluster, or you can connect more clusters in a bigger processor. You really the choice. So when we are in this is our choice today, to have a low power type of unit, very efficient. Obviously, we can group them. And what is interesting in that grouping, it provides an infinite scale. So you can put together like, I'm going to take one core because it's good enough, or I'm going to put on my card one cluster. But I can also take the processor and I can group the processor all together. I can build cards, PCI cards with 4 and more cards all together. Obviously, the limitation will be the power, but there's no limit in that. If you have enough power to have many of them all together, to provide more and more power. And it's linear scaling. This is where it's interesting. So linear scaling at the core level, at the cluster level, and at the group of cluster level. This is why it's really important, right, to have this scalability. So you want to treat a small edge, you're going to perhaps need one processor. You need to treat a medium edge, perhaps you need 2 or 3 of them. And you need to treat a big edge or data center, perhaps you're going to need more of those processors all together to deliver hundreds and thousands of stops, right? And the good thing is the way you program that is the same, because the software has been thought about scalability. And that's why when you think about storage and SPDK, scalability is very important. So just a summary here, when you think about many cores, DPUs, as it is named in the industry, even if we can do more, right? First, you need high computing efficiency. And I named some examples, right? We need those to treat those algorithms to manage data very efficiently, right? The thing which is more and more important is power efficiency. The example I've shown here can deliver the power I talk about within the range of 30 watts. Think about your x86. How many watts? If you look at the latest AMD or x86, we are speaking about 300 watts or plus. So this is like a 10x ratio. When it comes to managing edge, you don't have that much power. You need to be really efficient. Third, you need to be easily programmable. You need to have an open platform. And I think having this orientation around SPDK and others, we are thinking about C, C++, OpenCL for massively parallel compute. That's very important, right? You don't want to have something like FPGA with a specific language which is complex to program. You want something you find developers for, right? That's very important. Also, you want to be able to handle massive parallelism, because you have those many heterogeneous critical tasks to run at the same time. So you want to be able to run real time, but hard real time, not soft real time. You need predictability. And those manycore have been designed to be predictable. Obviously, you need low latency, right? When we are speaking about data management, we are referring to microsecond, not millisecond anymore. So predictability within that microsecond range is really which has driven the design of those DPUs. And as I said, right, scalability is very important. This is really the heart of the things. And when you think about storage devices handling more and more data, you need all those features. You don't want something which is closed. You need something with new algorithm because you have new type of data to manage. You need to enhance your compression algorithm because you have new factors or new models, etc. So you need to have this evolution, an open evolution, and community is very important for that. So if we look at the open standard and framework we are speaking about here, SPDK, you need some, you're going to fit, it perfectly fits here, right? And what we have done as an example is to use SPDK. We'll go into the details in the second part of this presentation. And what is well known in the storage industry as well, and how you treat things, is you need a control plane to control the devices, to program them, to manage them, and you need a very efficient and fast data plane, and you separate them. And this is what you have in SPDK. You have the control plane and you have the data plane. And here on our example, you remember that cluster orientation, 5 cluster. So one is dedicated to the control path running a Linux, very easy because you have a lot of drivers, you can handle SSDs, you can handle HDDs, and other protocols than just NVMe, OF, TCP, and Rocky. And we have a very light real-time OS, which is really the underlying things running a very efficient TCP/IP platform and RDMA UDP-based platform to support NVMe, right? And SPDK on the top of it. So SPDK and then the layers underneath, which I will go into the details of the platform. But this is really the success of that, right? It's not just SPDK alone. SPDK is important because it provides openness. It provides many modules available from the community today, but there are far more things underneath to make that combination, SPDK and manycore, a successful platform. So here, like a summary of the things you can do, right? You have a DPU hosted on a PCI Gen 4 card, 2 lines, 100 gig. Okay, so this is the hardware. This is nice. You've seen the results. You have seen the numbers. Completely open. What is important when it comes to build a storage target controller, right? You need easy management, and it's important to support standard Redfish, Swordfish, SPDK, or standards, and that's very important. This is completely widely opened to be included in many frameworks. When you think about OpenStack, when you think about Kubernetes, support Dockers, all those platforms now support SPDK, right? So it's very easy when you support SPDK to be integrated into those platforms. Obviously, you need very fast interfaces, right? I mentioned here 100 gig. That's the minimum, 2 times 100 gig full duplex to support NVMe, OF, TCP, and Rocky at the same time. We need to support the latest SSDs, Gen 3 and Gen 4 NVMe SSDs. That's the beauty of NVMe, right? NVMe runs over TCP, over Fiber Channel, over Rocky, over PCI. That's very nice. So it's really streamlined. And I want to make sure that we are not a blocking factor. We mentioned, the local consumption is going to be key tomorrow, right? I know many data centers where consumption is a problem. And when you think about the edge, 30 watt is something very interesting. And what is important is the combination between SPDK and your processor. So that's really, you have a low impact and you don't need an x86, right? You need to run independently. You need your card to boot in a standalone mode to control the drive and to deliver the services. And what are those services? When you think about all-flash array, you need data protection, you need resiliency, you need high availability, right? What if one drive fails? Obviously, you need RAID type techniques. If one card fails, you need failover. You need to have many of those cards in a chassis in order to provide a fully resilient solution for your data. And you can name other things: storage efficiency, the duplication, hole punching, zero detect, compression, are the things you can think about. And because you have a GPU which has been optimized to do so, is very easy to integrate them on and to treat data on the fly. And the latest one is security, right? When it comes to encryption, obviously when you have a DPU which has been designed with built-in features for security, it's really easy to add that at line rate, right? So in summary, this is a great combination of what could be done with SPDK, other standards like NVMe, NVMe OF, Redfish, Swordfish, PCI, all together on a manycore architecture. Thank you for the time today. I'm letting the voice to my colleague Remy to go into the details on how SPDK is running well on that type of architecture. Thank you so much. Bye-bye.